All right, welcome back. So announcements, we have Lab 1 due tomorrow, right? You can use it late if you like, in which case it's due Monday. We'll be posting solutions to homework 1. I don't think they're up yet, are they? Has anybody looked? I don't think they're up yet. But anyway, we'll post them. I did get the graded homework 1s back from the grader, so pick these up at the end. Remind me, okay, because I might forget. So someone remind me that they're up here, and we'll hand them out. The recitation, thank you, Umair. The recitation tomorrow will be map examples. So Umair has a bunch of Bayesian inference problem, Bayesian detection problems lined up that he'll help you work through. And yeah, I think that's the main thing. So I left these. I made these signs and I left them in my office. So I sent Umair back to get them. So so two ongoing problems, or I guess two of my weaknesses as an instructor. Number one, when I get excited, I start speaking rather quickly, and it can be hard for people to understand what I'm saying, especially if English is not your native language. This has been a problem since I started in 2006. Okay, I'm fine when we start, and then I get excited, and things go faster and faster. That's one problem. The other problem is that I just naturally do not press very hard when I write. That's true with pencils. That's true with chalk. So my writing can be a little bit lacking contrast. It's okay when the board is clean, but then as it gets erased, the contrast degrades. So I was just thinking about, since after Tuesday's lecture, how to address these, and what I was thinking of doing is just create signs, like speak slower, write harder. So I have a few of these. So what I was going to do, so I'll give Umair one set. So if you have the signs, then if it seems like I'm speaking so fast that you have trouble understanding what I'm saying, or you think other people might be having trouble understanding what I'm saying, then hold up the speak slower sign. If you can't read, or you think other people might not be able to read, hold up the write harder sign. So Umair has, those are the instructions. Umair has one set. I'm actually going to give another set to the cameraman. Right? And then the third set will just kind of float around, lecture by lecture. A different person can have it. So Patricia, you're the inaugural holder of the student set. So it's an experiment. We'll see how it goes. All right. I came up with these because I put, in my notes for the lecture, I often write, speak slower, write harder. And, I start lecture thinking that, and then I get into it, and I go into my old habits. So the signs are here to help me remember. Okay. Any questions? Okay. So today I'm hoping to finish Bayesian detection, and that will complete the probability background, and then we'll do we'll start the signals and systems background. Signals and systems background is a lot shorter than the probability one. So the probability one, takes 5 lectures thereabouts. The signal systems is much shorter, maybe 2. Okay, so let's recap where we were. So we did a bunch of stuff last time in the vein of Bayesian detection. So let me recap where we were. So the Bayesian detection problem is the following. You're given a joint distribution between two random variables, x and y. X you think of as the hidden random variable you're trying to learn or guess, and y is the observed random variable. Okay, so y represents all of your observations, and x is the thing you're trying to infer. Okay? So our goal is to design some function that guesses x from y, and I point out there are many ways of quantifying performance here. At least I showed you 2 ways. There are other ways as well. So one way is look at the probability that you're wrong. So it's the chance that g of y is not equal to x. It's a chance that your guess is incorrect. When x is discrete, that's the a natural metric. When x is continuous, that's typically too rigid, too uncompromising. So people use mean squared error instead. But we're interested in the discrete case because generally for us, x will be the data the bits that you're trying to send over the channel, and then y will be the output of the channel. And you're trying to infer the bits from the output of the channel. So x is discrete, and you're trying to guess the bits exactly. So this is for us, this is the natural formulation. Okay, so the core of the lecture last time was we went through the derivation of the optimal g. So what's the best function to put here to minimize your probability of being wrong? And we showed that the optimum guessing function is what they call the maximum a posteriori probability rule or map rule. Honestly, I don't know. When I wrote this up here, it dawned on me I don't realize what this P stands for, if it's posteriori or probability. And people call it the map rule, either way. And the rule is the following. So any guessing function is going to take a realization of y and then output a guess for x, right? So you accept a y, you output an x. Okay. So the way the map rule works is you know the joint distribution between x and y. That's important. That's part of the formulation. We assume we know the joint distribution of x and y. Okay. And then, so in particular, you can get the conditional for x given y. All right. You're given a y. That's like the channel outputs. You're given this number. Okay. You plug it in there. Now I have a function of x, right? Okay. So what I do is I find the value of x that maximizes this function of x. Whatever value of x achieves the maximum, that's my guess. That's what I guess for x. Okay. All right, using Bayes' rule, you can write this in other forms. So if y is discrete, you can write it in this form. If y is continuous, you can write it in this form. This is the same rule, okay? It's just written differently. And we show that this map rule minimizes the error probability. There's another rule that people use called the maximum likelihood rule, which is basically the map rule in these forms dropping the prior for x. Okay, so it's a little bit simpler of a rule. If x is uniform, okay, then these aren't really accomplishing anything here because the x that achieves the maximum with this here will be the same as the x that achieves it without it because this function is just like effectively a constant over x when x is uniform, right? Okay, so when x is uniform, then this isn't doing anything, and the map and the ML rule are the same rule. Okay. In general, if x is not uniform, then the map rule and the map rule and the ML rule will give you different answers in general. The map rule is the optimum one. The ML rule is a suboptimum one that you might want to use anyway because it's simple. Okay. So we then did an example. So this is like the first digital communication type problem that we look at in this class. So here's the setup. So suppose you have 1 bit to send. Okay. And you send this by encoding the 1 bit into like, a voltage. Okay, and so like one sample. The 1 bit gets encoded into one sample. Okay, that one sample gets sent over the ComCloud server. And what comes out, okay, is the sample corrupted by noise. And then the goal at the receiver is to, observe the channel output and then guess whether the bit was 1 or 0. Okay, so this is a rudimentary digital communication problem. It abstracts obviously a lot of stuff away. Okay, in reality, you have synchronization issues. You don't know which sample to pull out at the receiver. You get a bunch of samples. How do you know which one's the right one? The ComCloud channel doesn't just add noise. It also filters X and stuff. So, there are many things we're ignoring here, but start simple. Okay. So anyway, this is the model. You have a bit that's Bernoulli P. So it's 1 with probability P and 0 with probability 1 minus P. And the transmitter, the encoder, okay, takes the bit and maps it to either +1. I think I did the other way around on Tuesday, right? Let me fix this. I think it was +1 if the bit is 1 and -1 if the bit is 0. Okay. That voltage gets sent over the channel. The channel adds independent Gaussian noise to it. Okay, and we found that the map rule for this case was to take the channel output realization and just threshold it. If it's above this threshold, then you declare the bit was a 1. If it's below the threshold, you declare it was a 0. Okay, and the ML rule is just comparing y to 0. So just put a 0 here in place of all this stuff, and that's the ML rule. Okay, in general, if you have the map rule computed for an arbitrary prior distribution for x, if you just plug in the uniform distribution for that, then you'll get the ML rule. So usually if you're asked for both the map and the ML rule, usually you compute the map rule first, and then just plug in a uniform prior for x, which in this case means taking p to be a half, and then that whole thing zeroes out and you get the ML rule. Okay, you can also just start right from this and compute. You'll get the same answer. Okay, so when we left off, we were looking at the error probability of the map and the ML schemes. Any questions so far? Okay. Let's look at the error probability. So we know the map rule minimizes the error probability, but what is the error probability? Right? What is the optimal error probability? So that's the chance that G map of Y is not equal to X, right? That's the chance that your guess is, or B, I guess. I think we formulated it as guessing B from Y as opposed to X. I mean, they're kind of the same thing, right? If you have a guess for X, you can translate it to B and vice versa. Okay. So I think we started this calculation last time and didn't finish it, so let's continue. So I expanded this using total probability. So we have a chance that B is 1 times the chance that our guess is wrong, given that B is 1, plus the chance that B is 0, times the probability that our guess is wrong, given B equals 0, right? All right, now given that B is 1, our guess is incorrect if Y is below the threshold, right? So this event here is equivalent to the event that Y is below sigma squared over 2 log 1 minus P over P, right? Given this event is the same as this one. Likewise, given B is 0, we'll have an error if Y is above the threshold. So this event is equivalent to the one in which Y is bigger than sigma squared over 2 log 1 minus P over P. Okay? I'm going to do one more step in another color. Okay, Y is always X plus Z. Okay? Luckily, I have many colors up here. Okay, next step. Given B is 1, X is 1, right? Given B is 0, X is minus 1. Yeah? Okay. At this point, if you piece this all together, Z is the only random variable left here, right? This is the event that 1 plus Z is less than this constant. Okay? So this is a probability totally in terms of Z now. Z is independent of B, right? Because B and X are basically the same thing, and we said X and Z are independent. So this condition is not doing anything, neither is that one. Okay, so what do we get? Chance that B is 1, we call that P. And then I have the chance that Z is less than minus 1 plus the threshold plus 1 minus P times the chance that Z is bigger than 1 plus the threshold. Yeah? Okay, so this is a probability purely in terms of Z now. Z is a Gaussian random variable, 0 mean, variance sigma squared. We have 2 events involving Z, right? Okay, so this is something to express in terms of the Gaussian CDF. There's a particular form we usually put these kinds of calculations in, these answers in, to allow one to easily compare like different schemes. Okay? So there's kind of a standardized way of expressing this. I mean, at some level, we're done. I mean, like analytically, you can't really simplify it much more than this, unless you, I guess you can, write it down symbolically in terms of the Gaussian CDF, but at this point, if you want a concrete answer, you've got to numerically integrate it. But when working analytically, we tend to put it in a different form to allow easy comparison with other similar results. So for that, we use what we call the Q function. So the Q function defined as follows. Integral from x to infinity, 1 over square root of 2 pi, e to the minus t squared over 2 dt. Okay, I can just define this function, right? So qx just defined like that. What is QX in words? Like in English? So you can be the instructor, actually. So if someone comes to me in office hours, like several weeks from now, and says, what's the Q function again? I would not say, oh, it's integral x to infinity 1 over square. OK, I would say, yeah.
Isn't that the tail of the normal?
Yes, exactly. It's the tail, what they call the tail of the standard normal distribution. So this OK, take a Gaussian PDF, 0 mean variance 1. Take x. Integrate it. OK, so it's a chance that the standard normal is greater than x. Right? Chance of standard normal is bigger than x. And in the business, they often call this a tail probability. Because it's like if this was like a dinosaur, then like that's I don't know, the volume of its tail or something like that. All right, I don't know. Tail of a standard normal. OK, so let's express our error probability in terms of the Q function. Is Z a standard normal? Only if sigma is equal to 1, right? So in general, no. OK. Standard deviation is kind of important here. OK. So if Z was a standard normal, this would just be Q of this quantity here. Z is not standard normal, however. But I can make it a standard normal by normalizing, right? So if you just divide through by sigma, like that, Z divided by sigma is a standard normal, right? It's Gaussian, 0 mean. And its variance will be sigma squared divided by sigma squared, which is 1. OK? So this quantity is just exactly Q of 1 over sigma plus sigma over 2 log 1 minus P over P. See about this one. Inequality is going the wrong way. OK, so I guess I could write it as like 1 minus a Q function maybe. But actually, there's like a slicker patch to this. Multiply through by minus 1. That's certainly legit, right? Tell me about the distribution of minus Z. Yeah?
It's the other side.
What does the other side mean?
So instead of going x x to infinity, you go from negative infinity to 2.
That's true, but I'm saying, so this is a random variable, right? It has this distribution, right? That's the assumption. Here is a random variable. What is its distribution? It's the same, right? You've just taken the Gaussian density and flipped it about 0, and you got the same thing back, right? OK, so if I take minus Z divided by sigma, that is a standard normal. So divide through by sigma. OK, and this whole thing becomes Q of 1 over sigma minus sigma over 2 log 1 minus P divided by P. OK? So the overall error probability is little p times Q 1 over sigma minus the threshold plus 1 minus p 1 over sigma. Sorry, this isn't quite the threshold because we lost a power of sigma. So it's 1 over sigma minus the threshold divided by sigma. And then here we have 1 over sigma plus the threshold modulo that sigma factor. That's it. OK, so this is the same, the same answer we had up here. I've just massaged it and written in this Q function form. OK, so there's not a lot of like real value added going from here to here, except that we'll see every time we do one of these calculations, we'll put it in the Q function form, that allows you to easily compare like between two cases, which one has the bigger error probability and so on. So this is the error probability for map. For ML, it's somewhat easier, okay, because in ML the threshold is 0, right? So you just have 0 is 0. This whole thing is 0, 0. Okay, so you get P, Q, 1 over sigma, plus 1 minus P, Q, 1 over sigma, just Q, 1 over sigma. So it's a lot simpler. Okay, so if sigma goes to 0, the argument to the Q function is blowing up. So the error probability is doing what? Talk to me. As sigma goes to 0, the argument to the Q function tends to infinity. So Q, the error probability, what does it do? Go ahead. What? It goes to 0, right? So as 1 over sigma tends to infinity, then this line tends to infinity, and you get no mass in the tail, right? As sigma tends to infinity, we get Q of 0. What's Q of 0? 1/2, right? Q of 0 is going to be 1/2. Okay, so that, both of those extreme points you can probably guess just from the problem setup, right? So maybe easy to think about. This doesn't depend on P, so maybe it's easy to think about the P being 1/2 case. So if sigma goes to 0, the channel has no noise, right? So you'd expect there'd be no probability of error because the channel isn't doing any harm, right? As sigma goes to infinity, then the channel is like clobbering everything with its noise, and so you can't do better than just like randomly guessing at the decoder. You just flip a bit, or just flip a coin, and let that be your guess. That'll do as well as using the actual channel output. Okay, any questions about this example? Okay, let's look at a more complicated example. So sending one bit over now multiple samples. Okay, so we're still sending one bit, but now the encoder is going to take one bit and map it to like a bunch of samples, a big wave file. That'll go through your channel. You'll get a big wave file out, and you want to detect which bit was sent. Was it a 0 bit or a 1 bit? Okay. So our bit to send is the same as before, Bernoulli P. Okay, and the transmitted signal now, instead of being +1 or -1, it needs to be a whole signal, right? It has to be a vector, a wave file. So we'll have some fixed wave file we call A0, some fixed vector that we send if we're trying to send a 0 bit. And we have some fixed vector I'll call A1 that we send if we're trying to send a 1 bit. Okay, so if you want, you can think of these as wave files. You have like audio recordings. Okay, so if you want to send a 0 bit, you have this one audio recording, you send that. If you want to send a 1, you send this other audio recording. Okay, so if think of it as to send 0, you send this like, I don't know, Adele song, and then you have a Beyonce song you send for 1, or who are the dueling like rappers? It's like Nicki Minaj, and who's the other one? What's the name? It's like Remy something? Remy. Okay, yeah. I don't know how to pronounce them. I just read them on like web pages. Okay, so in your mind, you have like 2 songs you're going to play. If you're trying to send a 0 bit, you're going to play one song through the channel. If you're trying to send a 1 bit, you'll send the other song through the channel. Okay, at the receive side, you're going to get the song that was sent through, corrupted by noise. Okay, so the channel output is y. We'll call it y equal to x plus z. Z independent of x. And we'll assume z, Gaussian zero mean, that's a vector now, and covariance matrix sigma squared times identity. Okay, so in words, it's helpful to translate math into words, right? So in words, the channel adds independent noise to the signal. Okay, the noise is Gaussian, it's zero mean, it's IID over the samples. Each sample has variance sigma squared. Okay? So our job then is we observe y, and you want to kind of automatically detect whether the 0 bit was sent or the 1 bit was sent. Okay? So, at first blush, this might sound like a problem that'd be sort of trivial for a human to do, right? I mean, okay, you add noise to it, and I listen to it with the headphones. I can tell whether, well, actually, I couldn't tell whether it's Adele or Beyonce, to be completely honest with you, because I don't really listen to their music. But, presumably, if you pick those songs, you would know which one's which, and then you'd be able to determine the bit, right? So the challenge here is, we want to do this like automatically. We want to develop an algorithm that will do it. We want to do it optimally. Okay, so not just something that works in the typical case, but gives you the best possible performance, even when like the noise is high. So for a human, this might be relatively easy when the noise variance is low, because then you're basically just hearing the song with a little bit of static on top of it, right? But it's when the noise is like very loud, very strong. Okay, it can easily swamp the song, in which case it can be hard for a human to pick it out, all right? But the map algorithm, okay, actually can find it better than a human can. Okay. So, okay, so the question is, what's the optimal decoder or optimal receiver? So by the way, when I work with students in office hours, oftentimes, like given a problem like this, they'll just say, like, I don't know where to start. And I always say, actually, for these problems, you always know where to start. You just write down the map rule. Write down the map rule and then simplify it. Okay? There's like a real recipe for these problems. It does not require a great deal of creativity. So first step, just write down the map rule. Okay, so there's our statistic for 0. Here is our statistic for 1. Okay, given any y, i.e. given any wave file that you receive that comes out of the COM cloud, okay, you plug it in here, you're going to get a number. You plug it in here, you're going to get a number. If this one's bigger, you say 1 bit was sent. If this one's bigger, you say 0 bit was sent. That's the way map works, right? Okay, let's simplify this. Suppose we want to actually implement it in MATLAB. So what do these functions look like? So this we know. This is 1 minus p, and that's p. Sorry, this is b. X is not even a scalar in this problem. It's b right here. Sorry? Okay, so given b is 1, what can we say about y? So given b is 1, y is going to be a1 plus z. So therefore, y will be Gaussian with mean a1 and this covariance. Likewise, given b is 0, y is Gaussian with mean a0, covariance sigma squared times I. Okay, this is analogous to what we had in the scalar case. All right, so unfortunately, we need the multivariate density at this point to proceed further. So let's write that out. Okay, so if given b is 0, y has mean a0 that. And then for the one side, I have a very similar quantity. With A1 in place of A0. Sorry, what am I missing? I'm missing something. P, right? This thing with the arrow, right? P, 1 minus P. So let's put these in. So P right here, 1 minus P, right? Otherwise, it's the ML rule, right? Otherwise, it's the maximum likelihood rule, the one that doesn't even have those priors there to begin with. Okay, so for purposes of comparison, this denominator is not doing anything. So you can drop all that. All the action is in the exponent, so it makes sense to take logarithms. So take log of both sides. And we'll get log 1 minus P over P minus 1 over 2 sigma squared. I have the distance from y to A0. And we compare that to minus 1 over 2 sigma squared, the distance from y to A1 squared. People with me? All right, I'm going to multiply through by minus 1. That flips the inequalities, right? So what was 0 becomes 1 and vice versa. Let's multiply through by 2 sigma squared as well. So those are gone. And what we're left with is the following. So you have the distance from y to A1 squared minus the distance between y and A0 squared. And we threshold that. Against, I guess, minus. I'll write it as 2 sigma squared log of P divided by 1 minus P. Is that right? I'm a little worried that I got 1 minus P over P instead of the other way around. Okay, my notes are actually not very helpful on that point. Yeah, I guess it just depends which side you put it on, so it's kind of arbitrary. Okay. So that's the map rule. The ML rule is even simpler. This is usually the case. So 2 ways of deriving the ML rule. One is to drop these priors and go through the whole calculation. So just put 1 and 1 here. Okay. I also said if you solve the map rule for arbitrary prior distribution, you can plug in the uniform prior and then just pull the ML rule out of that. So we can also just choose P to be half, in which case you get log half over half, which is 0. So you end up just using a threshold of 0. So the ML rule, take the channel output y, compare it to A1. Like, look how far it is from A1. Look how far it is from A0. Okay, and map to the closest. Okay, I just chose P to be half in the map rule. This is what you get. Okay, so in words, And the way this works is you're the receiver. You're going to get a wave file. We can think of that as just a vector. Right? It's an audio recording. Okay? You have these two songs. You have whatever. You have Bach and you have Brahms, right? So you take the received wave file. Okay, so view it as a vector. View each of these two recordings as just points in Euclidean space and just map it to the closest one in Euclidean distance. Okay, so view like all three songs, the two pre-recorded things that are the 0-bit and the 1-bit, and your received signal, which is one of the two plus noise. View all those just points in some really high-dimensional Euclidean space, okay? And whichever of the two predefined points your point's closer to, use that to decide what was sent. Okay, so pictorially, you have two vectors like this, A0. I'm going to make it more like that. A1, let's say. And you just take all the points closer to A0 and declare that a 0 was sent, and then over here you declare a 1 was sent. Okay? So that's the ML rule. You just take like the line that, take this line, take the perpendicular, have these two intersect halfway through. That's the ML rule. And then for map, it's the same thing. You're just biasing it in favor of one or the other, right? So you have a non-zero threshold over here. Okay, so you're sort of biasing it in favor of one side or the other. So for map, okay, you get a picture that's similar, just this line won't be necessarily at the midpoint anymore. It'll move one way or the other. As we saw last time, it can even happen this line ends up like way over here. Okay, so that if you receive the vector A0, like you receive the Brahms recording exactly spot on, you say it was Bach, okay? Because it's actually more likely in that case that the receiver, transmitter sent Bach and the noise pushed it to Brahms than they actually sent Brahms and the noise didn't disturb it, okay? So you would need the noise to be relatively strong and the P parameter to be quite biased for that to really work that way in practice, but in principle, that is a regime that can happen. Okay, we'll go on the picture. I'll say another way of seeing why that can happen is think about the case where n, the length of all these vectors, is relatively small. Okay, if the recordings are like 5 minutes long, okay, then the chance the noise, takes you from one recording and pushes you away to the other one, that's like ungodly small, right? But if you had just like 10 samples, it's like a split second, right? Then it's not out of the question that the noise over the small number of samples would be enough to push you from one waveform to the other, right? Okay. Let's see, we can simplify this a little bit by expanding the squares. So just take the map rule. Okay, so conceptually, this form is quite nice. You've kind of mapped to the closest point. That's not necessarily the way you implement it, though. And for certain special cases, it's helpful to expand these squares and simplify, as I'll show you right now. So just expand the squares. You'll get the length of y minus twice the inner product between y and a1 plus the length of a1 minus, I'm going to get the same thing now with a0 in place of a1. Okay, and we compare that to 2 sigma squared log p over 1 minus p. Okay, so I just expanded the squares. Nothing more, nothing less. I get cancellations, right? These do not depend on y anymore. Okay, not anymore. These do not depend on y, so let me move them over with my other constants. And we'll get 2 y transpose a0 minus a1. And we're comparing that to, I'll get a0 length minus A1, the length squared, plus this other threshold, 2 sigma squared log p over 1 minus p. Okay, and it makes sense to divide through by 2. That. Okay, so now we're just taking the receive file y, and we're projecting it onto the difference signal, right? We have these two possible transmitted signals, A0 and A1. You form the difference. Okay, so that's a weird song. Okay, it's like Adele minus Beyonce or vice versa. Okay, so that's a valid song, right? It'll play, you can listen to it. It probably would sound very strange, but mathematically you can do that. Okay, so form that signal and then just take the inner product between your receive signal and that, and threshold the result. We have grimacing. Yeah, it's probably not kind of the artist to take their songs and subtract them from each other and so on. But that's what the math says to do, so what are we going to do? All right, this quantity here, the inner product, we call a sufficient statistic. So see that name thrown around. A sufficient statistic is just any function of y from which you can compute the map rule. Any function of y, which might be a scalar, might be a vector, doesn't matter, any function of y, from which we can compute, let's not do vectors, from which we can compute the map rule. It's just terminology. Is y itself a sufficient statistic? If I have y, can I compute G map of y? It's not intended to be a hard question. Yeah, you plug it in. Okay, if you have y, then you can compute this. I mean, we're assuming all in the background. We're assuming you have the joint distributions. If you have the joint distributions, then you can compute G maps. That's always assumed. Okay, the question is, do you have enough information about the channel output in order to compute the optimal guess? Okay, so if you have y, certainly that's true. So y itself is trivially a sufficient statistic. It's not a very interesting one, however. Here is a more interesting sufficient statistic. This is a function of y, right? You take y and you project it on this difference. Okay, that is a function of y, and it's one from which you can compute the map rule, right? If I know this quantity, I can just threshold it like this, and I get the map output from it. Okay, so hypothetically, if someone came up to me and said, I'm not going to give you y, I'm only going to give you this inner product, I would say, that's fine. I'll just threshold that, and it's as good as having y itself. Okay? So this is useful when doing analysis because it allows you to kind of this concept allows you to project the problem down to lower dimensional thing. Now this is all scalar, right? So every quantity here is a scalar quantity. Okay, so when you go to compute the error probability, it's a lot easier in this form than in those forms. It can also be useful for implementation purposes because if you think about the rule this way, okay, you might be tempted to kind of make a recording of the channel samples as they come out of the channel, store them in memory, and then compute these two distances, okay, both of which require you to pan through the entire set of samples. Okay, whereas this says you can just kind of pre-compute this difference, store that, and as the samples come in, okay, you can just multiply them sample by sample and just accumulate the result. Okay, and it would take I don't know, a third of the memory, right? Or yeah, a third of the memory roughly, right? Assume n is big, so this vector is big, this vector is big, this vector is big, this vector is big, right? Okay, so if you do it this way, then at least if you do the naive implementation of this, like you save y and then compute this, you've got y in memory, you've got a1 in memory, you've got a0 in memory, right? So you have like three long things. Here I have like one long thing, okay? And as y comes in, I just compute the inner product sample by sample and accumulate the result. So I guess you could also compute these sample by sample. Compute these distances sample by sample, right, and accumulate the result. So maybe it's like a half versus a third. But anyway, it's more efficient to do it this way. Yeah?
Is that supposed to be any function of y from which, or any function
From
of
which,
y
yeah.
I don't know, like which direction is it going?
Sorry. Yes, thank you. Other questions? Good. Let me point out one special case. Okay, so suppose A1 is 0. Okay? So my test reduces to y transpose A0 compared with, we have A0 length over 2 plus sigma squared log p over 1 minus p, right? I just took this rule right here, and I just said, let's consider the case where the A0 happens to be the 0 vector. Okay? So that's the test. So the English description of this scenario now is more like, I would think of it more in terms of like detecting whether a signal is there or not, okay, rather than trying to send a bit through a channel. So it's more like I'm the receiver. There's two possibilities for this signal that I'm observing. One is it's just pure noise, right? That's the A1 case. I'm observing just pure noise. The other possibility is I'm observing a particular fixed signal with noise. Right? Okay, and this is saying the optimal way of detecting whether you're observing just the noise or the signal A0 embedded in noise is to take your received signal, project it onto A0, okay, and then threshold the result. The idea is if y is pure noise, okay, then you have a bunch of like zero mean random variables here. You're summing up the weights. This is going to be kind of close to 0. Okay, so it's unlikely to be above this. Ignore this thing for right now. It's unlikely to be above this quantity. There's like the energy in the A0 signal, right? That's fairly large. Whereas if y was A0 plus noise, I'm going to get A0 transpose A0. That's the norm squared of A0, right? That's going to be bigger than this, plus a noise term, which hopefully would not be enough to push me below this thing divided by 2. Okay? This particular form people call the matched filter, I guess for historical reasons. So actually the reason they called it the matched filter historically is that like, once upon a time, if you had a signal you were trying to detect like this, you couldn't just like take a bunch of samples and put it in your like embedded system and then compute an inner product, and then threshold it. Like when a lot of this stuff was developed, like in the 40s, like there were no DSP, there were no ICs actually. So if you wanted to do something like this, you had to build like a linear circuit. Okay, one way of doing it was to build a linear circuit, like a continuous time linear circuit, whose impulse response was like the flipped version of a signal you were looking for. Okay, and then you just input your y into that thing, and as it convolved, okay, the convolution ended up, because this impulse response was a flipped version of this, the convolution ended up being like this inner product. And so you just let the filter run and then just take the output of the filter and just compare it to a threshold and then use that as your detector. So you had this, this filter whose impulse response was like matched to the signal you're trying to detect, hence matched filter. So applications, let me pose this to you actually. Where do you think this would come up, this particular form of the problem? Radar, yeah. That's like the classic application. That's actually where match filters were invented, was specifically in the development of radar. Okay, so so the way it works is, you have your radar antenna. Okay, you're going to send a signal up into the sky. That's the A0, and you get design A0. You pick it, all right? And then you wait, okay? And there are two possibilities. Either nothing reflects back, or very little reflects back, in which case all you observe is like the noise, and we'll talk about noise later, but the noise that's like kind of intrinsic to your receiver electronics, so internal noise to your receiver. That's one possibility. The other possibility is there's a plane up there, in which case your signal bounces off the plane, comes back, and then you observe A0 scaled, okay, plus the same noise. And you want to determine, is there something up there or not, okay? Nowadays with radar, of course, you want to do much more. How many targets are there up there? What is their heading? What is their size? What is their velocity, okay? But, when this was first worked out in the 40s, it was like, are the Nazis coming or not? If you're Great Britain, like it's, they're happy to just get like binary information, okay? So it's just like, is there something up there or no, okay? So then it's just a detection problem like this, okay? You just want to detect the signal coming back. How much of an A0 does it have in it? Is it just pure noise, or does it have an A0 component to it? So the way to do that is just project onto A0 and then threshold it. Okay, and here's where this, remember we talked about Bayesian versus frequentist, and assuming you have a prior probability for the two hypotheses. Okay, here's a good illustration of where that can get kind of dicey. So this is like, let's see, A1, A0 is the signal, right? So this is the probability that the Nazis are attacking. This is the probability that they're not. Okay, what numbers do I put here? Yeah, and this is like a life or death matter potentially, and we're just going to pick some reasonable numbers and put them in there. This is where frequentists get kind of bent out of shape. Okay, so there's reason for getting bent out of shape in that case, right? All right. Okay, let me do one more quick example because the punchline in this example is something we'll use a lot. Let me do one more example, and then we'll switch to signals and systems. Yeah. Okay. All right, so up to now we've been sending one bit. Suppose we send multiple bits. So detecting multiple bits using or over multiple samples. Okay, so B is now going to be a vector. So I'll just look at the 2-bit case. The extension to general numbers of bits will be pretty clear, I think. Okay, so suppose we have 2 bits. I'm going to assume they're IID Bernoulli 1/2. Okay, so there's no P anymore. They're not biased. We have 2 bits, unbiased. Okay, so our transmitter is going to send a different signal for all 4 combinations, right? So if you want to send a 0, 0, it'll have one waveform it sends. If you want to send 0, 1, another waveform, etc. Sorry, this is not written very clearly. So we have one waveform A00 that we send if B is 0, 0, 0, 1, 1, 0, 1, 1. Like that. Okay, and the channel is the same as before. Okay, so the differences between this and the previous example, we have 2 bits here instead of 1. But each bit is unbiased, whereas before we had this bias parameter p. Okay, so it's like more general or more complicated in one dimension, less complicated in another dimension. What is the optimal receiver? Where do we start? Map rule. Just write down the map rule. Like that. Now in this case, since the thing we're trying to detect is uniform, right? B is uniform over all 4 possibilities, right? So the map rule actually reduces to the maximum likelihood rule, right? Another way of saying this is that we don't really need that factor there because there's going to be a quarter in all 4 cases, so it's not contributing anything, right? Okay, so this also equals G of ML. All right, so we're going to plug in the same multivariate density, multivariate Gaussian density we had last time, like in the previous example, I mean. Like that, right? So I just plugged in for the Gaussian density. So given this vector b, y is going to be Gaussian with mean a sub b, right? Here, x is like a sub b, and covariance matrix sigma squared. Okay, now observe. People with me? Yeah.
Can you say again how you reduce the map rules to ML?
Okay, so ignore the blue cross out for a moment. That's the map rule, right? Okay. So in this case, P sub b is uniform, and that I'm going to get 1/4 here, no matter what I plug in for b. Assuming I plug in like, you know, one of these 4 possibilities, right? 0, 0, 0, 1, 1, 0, 1, 1. If you plug in like, you know, 5 and square root of 2, okay, then you're going to get 0 here. But assuming you restrict the max to just be over the set of possible bits, you're just going to get 1/4 here in all possibilities. So if the goal is to figure out which value of b maximizes this extra factor doesn't accomplish anything, right? It just multiplies it by 1/4 regardless of which value of b you pick. So it's effectively a constant you can just drop. And when you drop that constant, that is the ML rule by definition. Okay, another way of thinking about it is we know the ML rule is optimal, i.e. it coincides with the map rule when the thing you're detecting is uniform, and this thing is uniform, right? There are 4 possibilities. They all have probability 1/4. Okay, other questions? All right, this factor is not doing anything. The exp isn't doing anything either. If I just want to find the optimal value of b, and move it all into the exponent, drop the 2 sigma squared, and find the value of b that minimizes y minus a b, like that. Okay, so we saw this in the 1-bit case. When p is uniform, you map y to the closest of the 2 possible transmitted signals, right? Okay, so the point here is that carries on in general. If you have 4, in general, if you have any arbitrary number of possible transmitted signals, and your channel has this form, okay, then you're going to output the bit string whose transmitted signal is closest to your received signal. Okay, and they call this the minimum distance rule. Okay, so we have like a hierarchy of rules here of schemes. There's map, there's ML, there's minimum distance. map is always optimal. If the thing you're detecting is uniform, then ML is optimal. If the thing you're detecting is uniform and your channel has this particular form, where you have like some fixed transmitted signal plus independent Gaussian noise, then map and ML both reduce to minimum distance. Okay, so this is the most specialized of the three. Map is the most general, and ML is between the two. Okay? All right. Any questions on this? Any questions on detection more generally? All right. So we have a little bit of time to start the signals and systems review. I must say these signs, they're totally working. Because you don't even have to hold them up. As soon as I sense myself starting to talk faster, I say to myself, oh no, they're going to raise the sign. And I slow down. And so even if you're not raising them, just the fact that I know they're there, like, changes my whole mindset. Okay. So we're going to switch gears. And talk about signal systems. So probability, we put aside for a moment. We'll use it again. Don't worry. But for right now, we're going to talk about signal systems, linear time invariant system theory. So as with probability, I'm not going to do a complete review. I'm just going to zero in on the parts that we will use a lot that might not have been emphasized in your prerequisite courses, might not have even been covered, depending on what class you took and who taught it. So for probability, the parts that I emphasize because we use a lot and might not have been emphasized in your prior class, random vectors, and then Bayesian detection. For signals and systems, the part of the theory I'm going to review is what I call the finite length version of like the LTI systems story. Okay, so when you take a like beginning signals and systems class that covers transforms and convolution and all that, okay, you generally only look at signals that are like doubly infinite, right? They're signals that live over the entire real line, right? Or over like all the integers, okay? And all your convolutions are done like over the whole real line or over the entire integers, right? So it's all doubly infinite in time duration, okay? That's at least what you start out with, and maybe you go from there. In this class, we're more interested in like finite length versions of this. Like I create a signal with consists of 10 samples, and I send it through ComCloud, and I get like 10 samples back. And I want to know how are the output 10 samples related to the input 10 samples. Okay, so I have like a finite length version of this story I want to now understand. Okay, and it's not a trivial thing because there are edge effects that crop up when you consider like finite duration signals. Okay, the theory is very clean when everything is over the entire real line. Okay, but when you start doing like finite windows, then you get edge effects, basically. Edge effects crop up in the theory. In many other classes, those edge effects can just be ignored. Sometimes you don't even pretend they exist. You just find creative pedagogical ways of sweeping them under the rug so people don't even know what's going on. In this class, we cannot avoid them. Okay, the edge effects are important. In fact, I would say the really clever idea in OFDM, remember OFDM? It's the signaling scheme that this class is like designed around. The really clever idea in OFDM, I view as just a way to deal with edge effects. Okay? So if you don't understand the edge effects, then OFDM makes no sense. Okay? Because it's there to deal with edge effects. You've got to understand the edge effects. Okay? So we're going to do like LTI systems theory, finite time duration version. It's all going to be discrete time, all going to be finite time horizon. Some of these results I cover you might have seen before. I'm going to do them in the linear algebra version, in the linear algebra language. Even if you've seen them before, you might not have seen them in this linear algebra language. Even if you have, it'd be a good review. So first of all, there's a lot of definitions that we need to get out of the way. So let's just start with like a bunch of notation and definitions. So for this part of the class, we're generally working with complex vectors. Okay, we define the Hermitian of a complex vector to be the complex conjugate transpose. So take the vector and transpose, and then conjugate, or vice versa. We have two vectors. Then define the inner product to be x Hermitian and y. The length of a complex vector you define to be the inner product of the vector with itself, square root. Okay, you can check that that's always non-negative. So x and y are orthogonal if, naturally enough, the inner product is 0. If we have a complex matrix, again, we'll define M sup H, which we read as M Hermitian, to be the complex conjugate transpose, which again you can do in either order. And we'll say M is unitary if its columns, or equivalently its rows, are orthogonal and have length 1. So if M Hermitian M equals M Hermitian equals identity. So it has to be square in particular. So unitary is like the complex version of orthogonal, right? So a real matrix is orthogonal if the matrix transpose itself is identity. So its transpose is its inverse. Here the Hermitian is the inverse. It's like the complex version of that. All right, now there's a particular vector that we're going to use a lot, basically like a phasor vector. So I'm going to create special notation for this just because it saves writing. Okay, so E sub f is just a vector. Think of it as like a discrete time finite duration phasor at frequency f. So e to the j 2 pi f times 0. E to the j 2 pi f times 1 to e to the j 2 pi f times n minus 1. And in electrical engineering, we use j for square root of minus 1, right? So this is square root of minus 1 here. So these are complex. Make sure I'm not forgetting anything. Okay. So we're going to define the discrete Fourier transform, the DFT, in matrix form. Okay, so we're going to define it as just a matrix multiplication in the following way. Okay, so the IDFT matrix is just defined as follows. I'm going to call it W. And it's just the vector of phasors at frequencies 0, 1 over n, 2 over n, etc., up to n minus n over n. If you expand this out, this is what it would look like. So just take E0 over there and just copy it down. So e to the j 2 pi 0 for the frequency, then 0 for the time index. E to the j 2 pi 0 for the frequency, and then 1 for the time index. And so on. Okay, next column just has 1 over n for the frequency, otherwise the same. Okay, and then last column has n minus 1 over n for the frequency. So this bottom right entry, e to the j 2 pi n minus 1 over n times n minus 1. Boom. That's it. Okay, so I just took the E0 vector there and just copied it like that. It's the frequency that changes across the columns, and the, if you will, the time index in the phasor that changes down the rows. All right, so here's a question for you. Is this matrix symmetric? If I just flip it about this axis, do I get the same thing back? Let me ask this. What is the L-kth entry? Yeah. Like that? Symmetric? Yeah. Right? I mean, it's symmetric if WLK equals WKL. So that's certainly true, right? Okay, it is symmetric. However, if I take transpose of this matrix, I get the same matrix back. If I take transpose conjugate, i.e. if I take Hermitian, I do not get the same matrix back. I get a different matrix. And we'll call that matrix the DFT matrix. That'd be Hermitian. Sorry, this is underline matrix. All right, so, okay, I was going to try to squeeze in one last definition, but not a good idea. Okay, so we got the definition, the notation and definitions out of the way. So next week we'll do the signal and systems background. That will take probably like, I don't know, about 2 lectures. And then we can start talking about channel modeling, how to model the comm cloud, and then from there we can talk about actual communication problems. So I have office hours right now, if you want to chat about the lab or whatever else. And homework 1 I got back from the grader, that's up here, you can pick it up. And I'll see you Tuesday.